Hello everyone. The tutorial of this week is on concurrency control techniques. Before talking about what is concurrency control, why it's necessary, let me present you the agenda for this tutorial. We will do some recap about what you have seen in lecture. Then we will talk about two techniques for concurrency control, which are validation and snapshot isolation concurrency control. The last one is particularly more common because there are some scenarios when you want a very strict isolation between concurrent transactions. And lately we will talk about granularity of data items. So for example, sometimes it's useful to lock entire tables, while in other moments you don't need to lock the entire table for a certain transaction. So probably you need to lock a particular record, not the entire table. So we will talk about these scenarios when the granularity of the locking matters. So let's start doing some recap about what we have seen last week and also this week lecture. We talked about concurrency control. Concurrency occurs when you have two transactions happening simultaneously on a database and changing, reading, writing the same data item simultaneously. So this is when you have concurrency, and in such a case you would like to keep the isolation property. If you remember, isolation is one of the ACID properties that we want databases to implement. So in such a case, when you have simultaneous transactions happening at the same time and reading, writing the same item, and you want isolation, so then you need concurrency control. And such transactions, for example, one approach for implementing concurrency control, the first one is not very practical, is to keep them serializable. So keeping transactions running transactions in a serializable way is not very practical. There's a high overhead for doing so. So an alternative for serializable or transactions that run in a serializable way, it's running them in an interleaved manner. How is interleaved manner? It means that you run some operations of T1 or T2, doesn't matter. So you run some operations of one transaction, then you interrupt and read other operations of another transaction, then you interrupt and go back to the other transaction. If you have a transaction T3, then you start T3. So there are many ways, many order sequence, many ways of breaking down, choosing the order, which operations of which transaction should run right now. So this definition is a schedule. We saw this last week. But there are some problems that can arise when you have transactions running in an interleaved way. Not in serializable. Serializable is always correct. Always correct result, outcome. But when you run in interleaved way, there are some errors that can happen, like dirty reading. Dirty read, it means that you are reading data that has not been committed, and then after the transaction that changed the data might abort, rolling back. So you are reading data that, if in fact, will not reflect the state of the database after you abort that transaction. Loss updates, so you read an item and you update this item in transaction T1, and then transaction T2 meantime is doing the same. So T1 write a certain value for X, but then T2, after T1 is done, T2 overwrite the value of X with a new value. So you lost a certain update. So this is also a problem. And phantom records, it means that you are doing operations considering records that do not exist. You're ignoring records that do not exist, that will appear later. We will talk more about phantom records in this tutorial. So we'll talk about them again. But just to let you know that when you run transactions in interleaved manner, so this can happen. That's why we need concurrency control. What are the approaches for implementing concurrency control? There are several approaches. In the lecture, you have been mentioned at least three. The first one, it seems the easiest one, is the lock-based protocols. If you remember from operating systems, how you control the access to memory, for example, to resources, so you'll be probably familiar with that. So in binary, for example, protocol, a binary lock, for example, you have a certain item X, which might be a table, a record, or the entire database, or just a value of an attribute in one record. And then for this value, you have a lock which is either 1 or 0. 1, it means it's locked, so no other transaction can read or write X. But if the lock for X is equals to 0, it means that X is available. Then you can lock and then do whatever you want with X, and then you unlock, so it's not locked anymore, now it's 0, and then now it's free to use. So it's a very simple one, but also again there's a high overhead for doing so. Why? And sometimes this is an overkill. It's not always necessary to lock. Why? Because some operations, if you are just doing, you have many transactions just doing reading on X. So let's say T1 and T2 just read X. It means that locking probably wasn't not necessary. You're just reading or not even writing or doing anything. So an alternative for binary lock protocols is the share lock, exclusive lock. So share lock is this scenario that I just mentioned, T1, T2, they are just reading X. Nobody's really changing. So you don't even need to lock X. You can just allow all the transactions to run since they are just reading. Nobody will change. So you have a share lock. If you have one transaction writing X or changing its value, I mean, so it means that this is an exclusive lock and just this transaction have access to X. So this is an alternative to binary lock, is less overhead, but there is still some overhead. Then there are two-phase protocols. Here we have an example of two-phase protocols when you have, it's just a strategy for avoiding these problems, the problems that we mentioned before, dirty read, lost updates, phantom records. Is first you execute all the locks before you run all the unlocks. So you don't unlock any item before you lock all the items. So this is the two-phase protocols. Two-phase protocols so avoid some of the problems we mentioned, but gives rise to another problem which is not simple, which is deadlock. Deadlocks might happen. So for deadlocks, there are also lock-based protocols for dealing with deadlocks, which are wait and die, won't wait, cautions waiting, time series schemes. There are several approaches for dealing with such type of transactions. So for example, and wait die. Let's say you have two transactions. You have a transaction T1, which is reading write a certain item on X. T2 is waiting for T1 because it's reading X regarding there is a lock in T1. But T2, so T1 is waiting for T2, but T2 is waiting for T1 because of certain item database item Y. So T1 is waiting for T2 and T2 is waiting for T1. So we have a deadlock. So one of the approaches, for example, one of the protocols, we'll check, okay, who was the first one? Let's say T1 is a node transaction. Since T2 is a younger transaction and it's causing the lock, so in this case the database gives its permission to T2 to die. It means the database gives permission for T2 to die, but it's not a really bad decision, because T2 will be restarted later with the same timestamp from the first time that you asked to execute T2. But it means basically, because of you have here deadlock, you choose one of the transactions, which one will depend on which scheme you are using, and which will be executed later with the same time schedule. Why this matters? Because there are some other concurrency control methods where the timestamp when you ask for a certain transaction matters. In the next protocol, exactly the scenario that we are talking, when you have a timestamp control. So if you have a scenario of transactions that are trying to access a certain, you don't have necessarily a deadlock. So let's say you have just transactions that are accessing the same item X. So you lock in T1, T2 wants to lock to read here, and T2 wants to have access to read or write in the same data item. So what happens? The older transaction is allowed to wait. You postpone the younger, restart later with the same timestamp, or vice versa. And there are several rules here for identifying who should stop. Not necessarily the older transaction. There are some situations where the younger transaction should wait, or you postpone the older one. So there are several schemes here. So here's just an oversimplification of what the timestamp protocol really does. Then we have multi-version concurrency control techniques. This is particularly important, this one, multi-version concurrency control techniques. When you keep copies of the old values of the data item when this item is updated. For example, you have two transactions accessing, let me change the color. Okay, so I cannot change the color. So let's say you have two transactions trying to make some change, transaction T1 and T2, trying to make some change on a certain item X. So T1 will change X, will read and try to change the value of X, for example, the number of available seats in a certain flight, so in your database. T2 is trying to do the same, trying to book not just one but two seats, for example. That's a hypothetical example. So what happens in multi-version concurrency control, which is typically implemented in some databases? So T1 will make a copy of X. T2 will have another copy of X. T1 will make the changes on TX in data item X. T2 will keep changes on the same but on its copy, and eventually T1 will commit X, T2 will eventually commit X. So there is some control to avoid that loss updates happen. But the main point is you keep different copies, and then after you will verify if a certain copy, this might never even change, but if it changes, then you verify if which changes were applied for the original X compared to the original X, and then you decide either to abort the transaction or re-execute the transaction, but instead of using x, the original x, you use the new value updated by t1. Or yeah, so these are the two options that the multiverse concurrency control you'll face later. And why I'm saying this is important, because some databases, including Postgre, MySQL, maintains data consistency by using multiversion model. So you can find this information in the official documentation of Postgre. Here's the link, and you see here, unlike traditional database systems which use logs for concurrency control, so traditional databases use this one, but different of them, Postgre maintain data consistency by using multiversion model, so MVCC, for providing transaction isolation. So you'll see this in the documentation. Now you know what it means. So this is traditional databases. I don't know which traditional database, probably SQL Server, Oracle, IBM DB2, and here we have Postgre. One thing I didn't mention, this is important, there are some levels of isolation, so different level of isolation. For example, you can have a certain transaction T3. Let's say you have a certain transaction T3, and you don't care read information. You want always the most up-to-date information, the most recent information. Doesn't matter from transactions. Doesn't matter if it's committed or not. You just want the newest information. Doesn't matter if it's even committed. So you want to read data even if it's not committed. So this is a possible level of isolation, and such a level you are taking risks. You can read dirty data, you can non-repeatable read, so this I suggest you read the documentation, it's not hard to understand, and phantom reads, again we will talk about this later. So this is the worst level, the lowest level of isolation. The opposite way is the serializable. Serializable is, for example, you run all the operations of T1 before you run all the operations of T2. This is the best one, always correct, although it implies an overhead. There is no possibility of dirty read, no repeatable read, and phantom read. So there's no possibility. So PostgreSQL offers read commit, this one, and serializable. Can you change it? Can you set the level of isolation? Absolutely. We will see an example. So this is what you have been told during the last week and also the lecture of this week. Let's see some examples of the implementation of levels of isolation. So hopefully now you have a good idea. Of the general picture, the overall picture of what concurrency control is, when it's necessary, and which problems we are trying to prevent, the possible levels of isolation, and which ones are implemented in Postgre. So if you are curious about other databases, you can do your own research. But it's important for you to know that there are different levels of isolation that can be implemented in different databases. How to implement concurrency control? There are some alternatives. You have seen 3, you'll see more 2 in this tutorial. Standard databases mostly implement locked-based data protocols. So there are some alternative schemes, not all of them, but some alternative schemes that might be implemented in the databases. So from the more strict with high overhead to less strict with lower overhead, but also with some possibility of poor performance. You queue some transactions to avoid some problems. You allow some transactions to die and restart later. Use timestamp for that. and there's a full protocol based on just on timestamp, and multi-version concurrency control, which is used in Postgre. So hopefully you got a good idea of protocols, of concurrency control protocols are in theory. But how does it connect with the practice? How does it look like in a query if you want to implement such a control? Because there are some default configurations, the default isolation level, for example, which is read commit here in the case of Postgre. So there are some default information, some default configurations. But what if you want more control of the level of isolation you want? You are doing something really dangerous, something a query or an update which you want to guarantee a high level of isolation. So how do all these things look in practice? So let's take a look. So here what you have is you have two transactions happening simultaneously on the database. So in one screen you have transaction 1, you have another screen transaction T2. So you start to run transaction T1. So in SQL Server, one thing you can do is you can select part of the query and run just this part of the query that you want. So imagine the scenario, you start what you are doing here, in fact, you are simulating a schedule when you do it like this. So you select this part of the query T1 and then you press F5, because this is how you run queries in SQL Server. And then what is going to happen? You are setting the isolation level to serializable. So serializable is very strict, very strict. You will not be able to change data items in other transactions while you're using this data item in this transaction T1. In our case, the data item is a table inventory, and you are setting some attribute which is hidden here behind this comment to a value equals to 1, probably item in stock. So we'll change this value from this table and this row, this particular row. So you are changing, but you don't commit. So basically when you are locking for read, so you're locking the resource. In this case the resource is this column from this table in this record, while T1 is running. So T1 is locking this resource that I'll call X. You don't commit. So you don't commit, you are running just this part. Then you come to transaction T2 and then you try to run everything. So we just try to run the full T2. Remember, you didn't commit T1, so you did unlock X. And T2 is trying to read X. What will happen? You'll be stuck in executing query. In this case, it doesn't. Here is not correct. It's not query executed successfully. Instead, the message that you have is stuck in query executing query. This is what you're going to have. T2 will not complete, we will just be stuck. But then if you alt tab, go back to this window, and then you run the missing instruction, you commit the transaction, then automatically T2 will change from stuck in executed query to done, or query executed successfully. Then it will be completed. So you see, T2 could not be complete until T1 is done. Until T1 unlock that the database item X. In this case, this column, in this row, in this table. Why? Because you select the highest isolation level for your query. And why you are doing so? Because your application, your problem, your domain, your client wanted to certify that this change has a high priority and no other read or write could be done. We are just reading, we are not even changing anything. We are not, so no read, nothing could be done until this update is fully committed, fully done, fully complete. So when you go to your company and you need to implement such type of query, sensitive information, so be aware of isolation levels and the available isolation levels in the database that your company is using. Here you have more information about how to set. In this link you will be able to find more information how to set the isolation levels of your transactions. So this is a good practice, just a good example of to illustrate the topics that we haven't seen before. Now let's continue and see other two methods for implementing concurrency control.
Now that you have a good idea what concurrency control is, in theory and in practice, we have seen three methodologies for implementing concurrency control. Now we will see two more in this last part of the tutorial. So let's talk about validation or optimistic concurrency control. So what we have seen so far about the methods for implementing concurrency control before? We have seen mainly locking, timestamp ordering. These are two concepts utilized for implementing concurrency control. These are the main tools, not protocols, the main tools for implementing concurrency control. Locking, timestamping. For example, in locking, you do a check. Either a certain item can be accessed or not, for read or write. So you check before you access a certain item, or you try to access a certain item. In timestamp ordering, again, you check against the read and write timestamps of the item. So you see, before you do some operations, some read or write an item, you check the timestamp of the transactions on that item. So the keyword here is you always check for safety what you are doing if you can access a certain database item. So you always check before. Because you are checking before, there is some minimal, but there is some overhead for doing so. There is some overhead. It's minimal, but there is. So this protocol for implementing concurrency control, it's often this called validation or optimistic concurrency control, is often used when you want to get rid of this overhead. And how does it work? How do you avoid or prevent this overhead? So you make it, let's say you are using X, Y, and Z database items. So you don't check before you read or write X, before you read or write Y, before you read or write Z. You don't check if you can or not. What do you do? Before the transaction starts, you make a copy. When the transaction starts, you make a copy of X. So you are working on X prime, Y prime, and Z prime in memory. And then during the rest of the transaction, you work on the copy, not on the original database items. And this is the phase one. Then after you do all the operations of the transactions, you run the validation phase. Phase 2. When you will validate if your updates on these items will violate or not the serializability with the other transactions. So you validate if whatever you did was illegal or not. So why you minimize the overhead? Because before you read X and then do some operation, then you before read or write Z, before read or write Z, you always check. So do something, check. Read this guide, check. Read Z, check. You check before. Unlock, check again. So what you're trying to do is to do all the checks at once and at the end of the transactions. So you make a copy, you start to work on a copy without checking because it's just a copy. After the transaction is over, then you will do all the checks. And hopefully, that's why it's optimistic version control, hopefully it will not violate any condition necessary to implement serializability, which is a property that we seen the last week, is a way of guaranteeing that our transactions will have a right execution. So, and which conditions are these that should be checked? Well, we don't need to put a lot of effort here on memorizing these conditions, but there are three conditions that this step of the validation step does. Basically, you check if a transaction TI, which runs after a certain transactions TJ, you will check if TJ, if its write phase, transaction TJ completes its write phase before TI starts the read phase. So TJ is writing a certain item X, but it completed before TI starts its read phase of item X. TI start. This is what's condition number 1. Condition number 2. TI starts its write phase after TJ completes its write phase. So it's similar. TJ completes the write phase. It's similar. TI starts the write phase. This is one difference. So here is a write phase, but here's a big difference. The read set TI has no common set, element with write set of TJ. It means that TJ was writing elements that TI is not reading. And the third condition, both read set and write set have no items in common. So this is very optimistic. So we basically are checking or validating the interference between TI, transactions TI and TJ. Again, the conditions are very intuitive. We don't need to memorize them. So basically, we are checking the interference between the transactions when read or writing a certain database item. So we check if it completed before the other one starts to read, or if the other one, if it is completed and the other starts to write, we check if there's a read or write, which is characteristic of conflicting operations, if you remember from the last week. Conflicting operations. So this was the validation or optimistic concurrency control. So we implement two phases. One is work on the copy, and in the second phase, you start to validate the changes that you have made. And hopefully, none of these conditions was violated, and then you can just reflect the changes that you have done in memory to this. That's why it's a optimistic concurrence control. Finally, the last approach for implementing concurrence control in this one is really interesting is the snapshot isolation. It's used by Postgres and other relational databases like Oracle. The snapshot isolation, the concept is very simple. You like take a picture, kind of take a picture or a snapshot of the data items that you are going to read based on the committed values before the transaction starts. So the transaction is starting. You take a picture, you take a snapshot of the committed items, how they look like, and then during a transaction, either you work with these values for the data items. It doesn't matter if later after the picture another transaction PJ just committed a new value. You ignore this new value, you are working just with this snapshot that you took at the beginning of the transaction. So your current transaction TI will only see records that were committed in the database at the moment it started. If later something else happened to that database item, you ignore it. You consider just the committed information when the transaction started. Let's see an example in practice how it looks like. So you start setting up the snapshot isolation. So this is the level isolation we're using, so you start setting up the snapshot isolation. Then you start to run T2 without committing. So you start to run T2, just this part. So you set the transaction level snapshot, you begin the transaction, you are not showing. Okay. So here in this is transaction T2, transaction T1. In T1, so you start to run T1 without committing. So you start to run T1 without committing. So you are changing the value of this item stock. It used to be, let's say, a certain value. You are set it to 5. Let's say it was to 6. So you just bought an item and then it went down to 5. So it was 6. It used to be 6 item stock. Items in stock used to be 6. But then in this transaction T1, you set it to 5. You don't commit. And if you perform a select here, select items stock for this certain ID of the inventory, you will see 5. So this is obvious. And if you run the select differently of the previous practical example that we saw, you will not get stuck in executing query because the other transaction is using or accessing the same item. You will not see this happening. You will not have this problem. Why? Because we set this snapshot isolation. So which value you're going to show? You're not going to show 5. Why? Because it hasn't been committed. You're not going to show 5. So which value are you going to show? The value of the picture, the value of the snapshot you took at the beginning of the transaction T2. So it was 6. This is the value that you're going to show. And then when you complete the transaction, this is what you're going to show. 6. there's just one observation here. Things still can go wrong if T2 tries to update the same database item. T1 commits here, and T2 tries to commit. That will not be possible. T2 will be aborted. So here it's okay because we are just reading. But in this case, if we try to update the same database item with a different family, so T2 will be just aborted. So this is the drawback of this approach. You can see more information about transaction about this level of the isolation in this website. Alright, this point is interesting. We talk about one problem of the snapshot isolation that you probably already noticed. The beginner side of the transaction T1, you take a picture, you take a snapshot of the current state of the database items you're going to read, and you're going to work with this version of the database items. If later or during the transaction T1, a certain transaction T2 updates and commits these items, T1 will ignore this, will keep working with this version of these database items. So what we get, not just this, the transaction 2 can add new records to the database, and T1 may never see these new records. How do we call this problem here, this scenario? We call this phantom records. Phantom records. This is one problem that might appear in the snapshot isolation for the cross control. This can happen. This is the scenario that was described here in this text. So this is one more anomaly that can happen for one more request control method. You see, there is no free lunch. You are going to use one of these models, one of these approaches for request control. There will be issues that you must address. These phantom records and not inconsistencies are very hard to detect. Very hard to detect. Why? Because it's hard to simulate it. You cannot debug it, so it's very hard to detect and to reproduce. So the most you can do is plan well and try to analyze the trade-off. What are the trade-offs? What can you prevent? You will sacrifice performance to get consistency and perfect isolation, or if you have billions of transactions happen per minute, so you will sacrifice consistency and to gain performance. So this is a decision that you need to take when you design a system. For more type of anomalies that can happen, not just for snapshot isolation, but for other request control methods, so you can read these papers. This is scientific literature on the topic, relatively recent, and also how to modify snapshot isolation to make it serializable. This is a challenge, right? So this seems a gold mine. So there's some research in this direction. Finally, the last point, let's talk about granularity of data items. So there is some hierarchy in data items. Here in terms of, imagine that we are talking about information on disk. All of this is on disk. This is disk, right? So in the disk you have the whole database. You can also have file value of a record, or field value of a record. So for example, here is a column age. Table student. You can also have tables. We have an entire database here. We can have entire files. I think this is file for a certain table. We can have disk blocks. Disk blocks, I don't know if it's represented here somewhere. Can disk blocks, purpose this one. Disk blocks for several records. You can have several records depending on the disk block factor. You can have just one single attribute of one record for the full record. So you see there's some hierarchy or granularity of the data items. So when you log the data an item X, what is X? It depends. The choice of the grain. The choice of the grain. Where is the grain? The choice of the grain will change the performance of your database. So let's say you are going to run an update statement. So update table student set age equals to 18. So what you are going to do here, you're changing all the records of the table student, all the records of the table student to have an age equals to 18. So which level of lock should you use? You could have, let's say table students have 1,000 students. You could have 1,000 locks per record. But then you can imagine the overhead of checking locks, creating the locks, and then checking individual locks. Probably here in this case, the smarter approach would be lock the entire five students. So nobody changes anything in the student while this transaction is updating the student. But if you add a condition where ID equals to 1, so in this case, this lock is a poor performance because no other change, no other transaction which does anything on the table student, any read or any write on students which are not this ID will be waiting for this transaction. So in this case, the database automatically selects the most appropriate record. In this case, could be either the entire record or just a lock on this particular attribute that will be updated. So the choice of the grain here changes or affects the performance of the concurrency control. There are different types of locks. So let's take a look at the different types of locks in Postgre. There are, for example, table level locks, so different types of locks for tables, and there are row level locks. So these are the two types implemented in Postgre. And who decides what type of the lock is used? So it's Postgre automatically manage the locks. So this is just some interesting information how Postgre decide the best type of lock or grain for the lock in its concurrency control. So that's all for the tutorial. Hope it was useful. We saw some theory about concurrency control. In the recap, we also saw some practical examples. Then we talked about the two methods for implementing concurrency control. And we talked about granularity and showed in Postgre how it looks like. Postgre scale. So that's all for today. So I hope you enjoyed and good luck in